Well, that was a rude interruption by potential spam. So, going back to this discussion here, when we look at this thing here, we say, like, okay, this is the definition of what it means to be equal. So, if I gave you, I mean, this is the most natural thing, though. It's not, it shouldn't be mysterious. If I gave you two different black box programs and asked you to prove that they always gave the same output, what would you do? I said, oh, and by the way, the inputs are natural numbers. Well, you'd start putting in natural numbers and checking. Okay, is f of 0 equal to g of 0? It is. Okay, is f of 1 equal to g of 1? It is, and so forth. Now, you might never finish testing every natural number, but you would find that if you ever find that f maps some number to a different value from g, then you know that they're not equal. So it turns out really this is called a semi-decision problem. You can semi-decision. If they're not equal, then you can find it using that method. Then there exists an n, which is a natural number, so that f of n is not equal to g of n. And you can find it just by keeping going long enough. But if they're equal, you're not going to ever find it because you just have to keep putting in more and more. You've got a black box. You can't see anything inside. Anyway, this equality is called extensionality. So how can we use it? Well, we use it to prove that functions are equal. And why is this important? Well, because if we can prove that functions are equal, we can prove that functional programs are equal. And that's a crucially important thing to do when you want to say, for example, replace one program by another that's more efficient. You'd like to know they do the same thing. So suppose that f and g are functions from int to int, and f of k is defined by f of k is defined by 2 times k, and g of k is defined by k plus k. Now, we'd like to prove that f is equal to g. By extensionality, we can show these two functions are equal if we can show for every k, which is an integer, f of k is equal to g of k. So choose an arbitrary integer, call it j, and now show that f of j is equal to g of j. Well, f of j, by the definition of f up here, is equal to 2 times j. But 2 times j is just equal to j plus j by the definition of multiplication. And j plus j is just equal to g sub j, which is defined up above by the definition of g. So the two things are equal. Okay, so there's some food for thought down here. We've shown that if A is a set and B is a set, then A arrow B is a set. But we also showed that but A arrow B is also a set. So we can put that in. So that means we can write down functions that have, for example, functions as the elements of the domain mapping to some other set C. Or to make it more concrete, you could have functions, we could start out with nat arrow nat, but then we can say, oh wait, that's a set, so we could put that here, and we could have nat arrow nat. So this is a function that's going to take an integer and return a function. it's going to turn out that this mechanism is crucial in functional programming. We can take a function as input and output an integer. We can take a function as input and output a function as output. And these are called higher order functions. And so that's something you may think about, and you may have run across it in the reading by now or not. I'm not sure. Okay.